everybody. I hope you all had a good lunch. I'm Shirley Tarboton. I'm a lead software engineer with Capgemini, and I'm going to be talking to you about decarbonising code. And I thought we could start with a quick game of GeoGuessr. Do you know where in the world this picture was taken? Well, some with mountains. Anyone else? Anyone from South Africa here? Okay, this is the Drakensberg Mountains in South Africa, and the tallest peak there is called Rhino Peak, and it's a place where my family and I love to go walking. I wasn't always that keen on nature, but I went on a school trip when I was about 11 years old with my class, and we went to a private game reserve, and we got to walk in single file silently through the African bush, trying to find animals. And we also got to take turns at night sitting around the campfire, watching out for predators. And that really sparked my love of nature. So that's why I'm really passionate about this topic, and why I think we need to do all that we can. So I know that as software engineers, developers, DevOps, we spend most of our time sitting at a keyboard behind a screen, and we may think that the only carbon footprint that we have is when we get up to make ourselves a cup of coffee. But the stats tell us otherwise. So let's take another look at what the stats say. Data centers use between 2 to 3% of electricity, which is actually more than the global aviation industry. Bitcoin uses 110 terawatts a year, which is as much as a small country like Malaysia or Sweden. And training and hosting one AI model produces 50 metric tons of carbon emissions. So we need to up our game to reduce the carbon that the systems we write produce. And our coding practices do make a difference. If we can get our code to run more quickly with optimal CPU intensity, utilizing less storage, we're going to bring down our CO2 emissions. Now, in this talk, I'm going to use certain words interchangeably. CO2e is CO2 equivalent. I'm going to use that interchangeably with carbon and carbon emissions and electricity and energy. And I know that some energy will obviously be coming from renewable resources, but even if you're using solar panels, those solar panels have an embedded carbon. So I'm going to use those terms interchangeably as we look to reduce what we can do. So let's start with some coding practices, and let's start with looping. On the screen, there are two blocks of code, and they achieve the same result. The one on the left is the high carbon or brown code, and the one on the right is green code. This block of code tries to find a booking reference on a flight. And the flight has got, an airplane has rows and it's got seats in rows. So the idea is that it goes through all of those to find the booking reference. Now, at the beginning of the block on the left, it allocates a not found to a bit of memory variable. And then it starts in the outer loop, iterating through the rows of the aeroplane. And then in the inner loop, it iterates through the seats in each row, and if it finds a reference, it updates the memory. And when both of those loops have finished, it returns the position. The block on the right, however, returns the position when that match is found and exits. So if we look at the number of times those two blocks of code iterate, the left-hand block will always iterate the same number of times, which is the number of groups times the number of seats. Whereas the one on the right-hand side will iterate a different number of times depending on where that reference is found. In a worst-case scenario, it'll iterate the same number of times as the block on the left. But on the best-case scenario, it could iterate just the once if the booking reference is found in the first row in the first position. The big O notation for those two blocks is the same. But in practice, the average number of times that block on the right is going to execute is half the number of times. So when you're choosing an optimal algorithm to run, you do need to look at the bigger notation. You also need to think about what happens in practice and to think about storage. Let's look at queries. On the left-hand side, we have some of the high-carbon query issues. If you're querying your repository in a loop, and if you're querying something like the size of the repository in the loop, you're going to be having a much higher carbon footprint. If that query almost always returns the same results because the data is seldom upgraded, you could do the item at the top of the right-hand side, which is you could cache the result of the query. On the left-hand side again, if you're passing around an entire data set, that's going to have a much higher carbon footprint than on the left-hand side. Sorry, on the right-hand side, if you just pass around a page on initial load and then load the rest of the data later. If you pass the data around and only filter at the application layer, that's a bit late. What we want to do is we want to try and push the querying as early as we can and do all the filtering as early as we can. I think we should talk about logging, because logging has a very high IO impact and therefore a carbon impact. If we log at the info level, every time we want to log, we're going to see that logging in production. And if we don't minimize our logging, we might find ourselves in the situation that I've seen on clients where some technician has had to go and clear the logs on a logging server because it's filled up. So what we need to do is to minimize our logging. When we're logging in our clusters, we'll see those debug and trace level logs. And we also could consider using some tracing tools if that's why we're using our logs. So we want to be able to diagnose problems. Having minimal logging helps us diagnose those problems, and using a tracing tool might actually help us even more. More on coding. What do the researchers have to say about coding? Well, Giorgio, Rizzo, and Spinalis say we should choose our data structures very carefully. And an example would be if you've got a number in your storage and it's a very small number, why not use an int? Why use a long? Sahin and Bunce say we should avoid the decorator pattern. They've looked at all the patterns and they've worked out that the decorator pattern has a high carbon footprint. Pereira says we should avoid using interpreted languages such as Python because it has a high carbon footprint. But personally, I think Python is great for a quick script. It's just things that we need to think about on the coding side. Now let's talk about testing. How do we test? Again, brown testing, green testing. I love the testing pyramid that has a lot of unit tests, less integration tests, and just a few end-to-end tests, because we know that integration tests are quite expensive in terms of how long they take us to write and also the resources they spin up. So the Spring Boot context takes a lot of resources. Just to move forward onto a bit of testing code that's been spotted in the wild. On the left-hand side is the brown code. On the right-hand side is the green code. Now, some context might be helpful. This was seen on an event sourcing system, where the aim was that there would be eventual consistency. So for the testers to test that events had been received, when their infrastructure was quite flaky, they decided to introduce a sleep so the test wouldn't fail. So there's a sleep of 2 minutes in the brown code, and that was in a test utility. So if somebody decided to run the set of integration tests that all imported that particular utility, they might as well go for a very long coffee or lunch while those tests ran. Using a tool like Awaitility means that the tests would potentially run a lot faster. Now, I haven't got time in the 15 minutes. I've got to get into the nitty-gritty of the difference between the carbon footprint of sleep and Awaitility, but it's certainly worth thinking about. Going back to this integration test and end-to-end test and unit test slide, integration tests and component tests are really important because they test those integration points. I have been on a project where the QA team did all the integration testing, and the tech lead said, don't worry about writing too many unit tests, because the end-to-end testing team will pick up the problems. But of course, that's far too late. We need to get those tests passing and all the edge case passings as early as possible. Another issue with testing is if every test team wants to orchestrate all the resources in their environment, and so they want a dedicated environment. If we can get those tests, end-to-end tests, running in the pipeline with ephemeral resources, we're going to see a better performance and a better carbon footprint. Something which we're doing more and more of is using pact or contract tests, where there's a pact broker which stores the contracts between services, and that's a very light way of integration testing. Okay, let's move on to tooling. I wonder what the carbon footprint of our IDEs is like. Have you ever been in a situation where you've spun up your application to try and debug something and potentially had to run a whole lot of Dockerized services alongside that, and then needed to share that in a collaboration environment with a colleague? My laptop starts to churn, and everything goes to pieces, and I could basically fry an egg on the bottom of it on occasion. So it would be really helpful to know what the carbon footprint is of those different tools, and I think we need to put pressure on our vendors to let us know. You can tell that your battery's running down, and some people might have gone to the situation where they've actually decided to use a virtual workspace for their dev work, and then you're running 2 machines, and that can't be great for the environment. Moving on a little bit to the other tools that we might use for monitoring. Monitoring carbon in production is something that vendors are now suggesting they can do. And one particular vendor mentioned that we could add monitoring of carbon to every service at an overhead of 0.3% and potentially save up to 0.3% by finding those carbon sinks. But that's too late. We need to spot our carbon sinks much earlier. So if we can shift our code analysis earlier, we'll pick up those carbon sinks. Now, there are tools out there. A Capgemini IT was working on a SonarQube plugin called GreenSight, which is now being merged into EcoCode, and that is for spotting carbon sinks early on. Another thing we can do in our pipeline is we can build native images, improving the performance and reducing the carbon footprint. And finally, the Green Software Foundation is working out their impact framework, which is a way to compute and report the environmental impacts of software applications accurately. And they're looking to all different groups for plugins for their impact framework, so that it is reflective of the different environments where it's running and helps different teams measure. Let's talk about hosting. High carbon hosting and low carbon hosting. High carbon hosting is probably where you're going to be hosting on your own bare metal boxes, running them 24/7, potentially having low utilization at different times. Obviously, moving to cloud gives you the option to be able to use a more green platform. But what can happen with cloud is that people tend to provision as many environments as they like, potentially oversizing instances. And here's an opportunity for us as software developers to make sure that we are auto-scaling, that we are right-sizing our instances, and that we're using ephemeral services when we're doing things like testing. A useful term is mechanical sympathy, which is how we make sure that our services are running at an optimal level. I've got some references here or further reading, if anybody wants to go and have a look where some of the figures came from in this talk. And if you have any questions, I'll be here for a little bit now, and you can come and find us, anyone from Capgemini, at our stand, which is B8. Well, think that went a bit more quickly than I expected, so we're done. But if anybody has any questions, come up to the front and happy to chat. Okay. Oh, go back to the references slide. Okay.